All right, here we go. Yesterday we were talking about Lewis diagrams, how to draw Lewis diagrams. Um, Sometimes you can draw a Lewis diagram and you might not be sure if it's right or not. This is going to show you how to decide if a Lewis diagram is correct. This concept is called formal charge. So, again, the purpose is to determine which diagram is more likely. Now, the way that you calculate, or what formal charge is, it's the number of valence electrons on the free atom minus the number of electrons assigned to the atom. Okay, so what does each of these numbers mean? Well, the number of valence electrons, you know what this is because this is easily found from the periodic table. Remember, it's the column it's in, okay? And then these guys are what we call the assigned electrons, right? The unshared electrons, this is lone pair electrons, right? Lone pair electrons, and half of whatever electrons are bonded to it. Okay, so we're going to calculate the formal charge for each element in the Lewis diagram. And what we are looking for is a formal charge of 0. If the formal charge is 0, then the likelihood that the diagram is drawn correctly is high. Okay, so goal. That's the goal. So we drew SO4 2 minus yesterday. We drew sulfate yesterday. When we drew it, it looked like this. And based on what you know, based on what I taught you, this is entirely correct because you're just following the procedure. Right? We said that's sulfate. But is it really? So let's go ahead and assign formal charge to each of the elements present. So we have two elements. We have sulfur and we have oxygen. Okay, so for the sulfur normally has how many valence electrons? 6. So it's 6 minus. And how many lone pair electrons are on this sulfur? 0. How many electrons are currently bonded to sulfur? 8. So what we have is 6 minus 4 for a formal charge of 2. Formal charges that are positive are generally not likely. Let's calculate the formal charge on oxygens. Now, all oxygens are identical here, so I only need to do this once. I don't need to do this 4 times. Okay, so oxygen normally has how many valence electrons? 6. And how many lone pair electrons are on any given oxygen? 6. Yes.
For sulfur, why isn't it 6 minus 2?
Sorry. Yeah. There were 8 here. My bad. Okay. So we have how many bonded electrons are on the oxygen? 2. So half of 2. So what we have then is 6. Our assigned electrons are going to be 7. So this is 6 minus 7, which is a minus 1. That's a negative charge. Now, negative charges are allowed, but it's got to be the most electronegative element. And in this case, oxygen is the most electronegative element. So the fact that oxygen has a formal charge of -1 is not so bad here, but the problem is we have an element with a positive formal charge. Positive formal charges are very, very unlikely. So we've got to fix this. We've got to redraw the Lewis diagram for sulfate in a way where we get our formal charges as close to 0 as possible. So I drew these really large here. I'm just going to slide this over. Okay, so I present to you this. sulfur. We got 4 oxygens. So we've got 32 electrons. I present that. Okay, so let's reassess. Let's recalculate our formal charge for sulfur. 6 minus 0 plus half of 12 equals 0. That's a pretty good formal charge for sulfur. Let's evaluate the oxygens. Now, there are, based on this diagram, 2 types of oxygens. This is most likely a resonance case, but what we'll do is we'll take the oxygens A and B separately, and then we'll average them. Okay, so I'm going to call the double bonded ones oxygens A and the single bonded ones oxygens B. Okay, so for A, 6 minus 4 plus half of 4 is 0. So the oxygen A's come in with a formal charge of 0. That's good. The oxygen B comes in at 6 minus 6 plus half of 2 minus 1. Not terrible, but remember, it's not a full minus 1 because we have resonance. Then the FC averaged for all of the oxygens is really going to be 0.5, negative 0.5. And so this is what we are going to go with, because in this model we have a formal charges closer to 0 than we did the previous. If you ever end up with a positive formal charge, you've got to rework it. Now, why is this allowed? Why is it that we show sulfur here with effectively 12 bonds? What about the octet rule? What happened to the octet rule, right? Remember, octet rule says that each atom should have 8 electrons in its proximity. How come this one can have 12? Yeah, it has access to the D subshell, right? Sulfur's in the 3rd period. Any element in the 3rd period, 4th, 5th, 6th, 7th, has access to a D subshell. A D subshell is extra space where these extra electrons, these expanded octets, can reside. Yeah.
So we can just find the
Kinda. Now, as you do a bunch of these, you will realize there's certain patterns. You will start to pick up on the fact that oxygens like to be double bonded, right? And double bonding ends up to be a very stable state for oxygens. Okay. So if what you have drawn turns out producing a positive formal charge on any of the elements, start thinking about double bonds. Okay. All right, let's try the next one. XeO3. Actually, you try XeO3. See what you come up with. Any suggestions? Yeah, Anthony.
Go back all the oxygens to right hand on the axis and four on the
So like that? Okay. So let's take a look. Let's evaluate this. Do you guys see when we calculated the formal charge of the double bonded oxygen here on this side, that this turned out to be 0? So the oxygen here is the same scenario. So we already know the oxygen's formal charge is 0 here. What about the xenon, though? So for xenon, we've got 8. So the valence electrons minus the assigned electrons. There's 2 lone pair electrons on it, plus 1/2 of what would be 12. 2, 4, 6, 8, 10, 12. Yep, 12. So we get a formal charge of 0 on xenon this way as well. So formal charges of 0 are most likely. So even as odd as this looks, this is what we're going to go with. All right, unless there's a different scenario. Let's see. Let's see. How would it look if we had a single bond on one of the oxygens? So if it looked like this, all right, that's still 26 electrons. Oh, that would just, let's see, 2, 4, 6, 8, 9. Our xenon formal charge in this instance would be 8 minus 2 plus half of 10, right? So 8 minus 7 would give you a formal charge of 1. That's worse. Positive formal charges are no good. All right, so it's not this. Okay, let's do one more, because I feel like this is such a weird thing. We need a little bit more practice. I'm going to carve out some space here. Let's do formal charge for... No, do a simple one. Yeah, Mattia.
So can xenon have 14 as the
So it's super odd, right? So here is a lesson in higher level chemistry. Rules are only rules when they're convenient. Okay. You were taught certain rules because the certain rules at an introductory level cover the vast majority of circumstances. You get into the weeds, though, you start to have theories that compete with one another. Now, what I have taught you is what's called valence bond theory when you guys were sophomores. Okay, I didn't tell you the name, but that's what it's called. And there's other bonding theories called molecular orbital theory and band theory. So these competing theories all are attempts to address the shortcomings of other theories. So we are now entering into the limitations of valence bond theory, and now creeping into the realm of molecular orbital theory, and they're starting to overlap. And when things overlap, it's because there's a problem with one of the others. So molecular orbital theory is no longer in the curriculum anymore because the AP has decided they cut it out because nobody had time for it. So nobody was teaching it. And frankly, we don't have time for it either. But yeah.
Is it more accurate?
Depends on the situation. Is this color blue more like blue or more like green? It depends on the lighting, right? So it's all context. Now, I will say this. Xenon, the noble gases, xenon, krypton, argon, actually mainly krypton and xenon, don't you notice that it's weird that a noble gas is bonding here? Okay, so noble gases, they don't bond, generally speaking. They don't bond naturally. This would not happen out in a natural environment, but under controlled laboratory conditions, under artificial conditions, is when we see molecules like this form. I mean, we'd have to get this under some high temperature and high pressure in order to get this to form, right? Which means if it's not naturally occurring, it's not that useful to us, right? Especially, again, medicine, if it's not naturally occurring, you don't have to really worry about it because it's not something that the cell actually works with, right? So maybe it's not the best example. This is more so an example of showing you the mechanics of calculation, right? But for small molecules like ammonia, which is one of the most common molecules around, you should be able to calculate formal charge no problem. So let's do this one. So for the hydrogen, Lewis diagram first. All right, so for your hydrogens, how many valence electrons? 1. How many assigned electrons? Well, there's no lone pair electrons on it, and you're going to take half of what's bonded to it. So the formal charge on hydrogen is, 0. Nitrogen, 5 normal valence electrons minus the assigned electrons. Okay, well, it's got 2 lone pair electrons plus half of what's bonded to it, which is half of 6. So 2 plus 3 is 5. 5 minus 5 is 0. So this is a perfectly good Lewis diagram for ammonia. And really, it's actually the only way it could have been drawn due to the limitations of the size of nitrogen. You guys okay drawing diagrams and assessing formal charge? It's not that often that you're going to need it. It's just only in situations where there could be other permutations of drawing a Lewis diagram. All right, so don't think that you have to determine formal charge for every single molecule that you see. Really, when it comes in handy, what times you're going to probably need to do formal charge is when, let's say you have 3 elements, you're not sure which one goes in the middle. So that's an example of when you would use formal charge, or if you want to explain why it goes in the middle, or if there's double bonding involved, you need to figure out where the double bond goes. Okay? Those are the primarily where you see it. Okay. Next topic, bond strength. So the strength of the bond is determined by how much energy is required to break the bond. We call this bond enthalpy or bond energy. You will see it labeled as either. So take, for instance, a diatomic chlorine molecule. In order to break Cl2 and become 2 independent chlorine atoms, you're going to have to break the bond within it. Right? So that energy that would be needed is the bond energy. Now, bond energies are going to be positive because bond breaking is endothermic. Requires energy to break a bond. You want to snap a string, you're going to have to put some effort into it. You got to pull it. You got to put energy into it. Okay, bond breaking is endothermic. And this should align with what you know. We already talked about this. Bond forming is exothermic. Okay, so these two, you got to get them straight. Okay, so a little bit of review ties in here. When we talk about the enthalpies of reactions, right, delta H reaction, right, we've calculated this a number of ways back in our thermochem units. Here is yet, so we used this method before, right? The bond enthalpies of the bonds broken, I'm sorry, we didn't use this before. What you did use before was this. The sum of the delta H of formations of the products minus the sum of the delta H of formation of reactants. Right? This is what you guys use to calculate delta H reaction if you had an enthalpy chart. There's another way to calculate this, but it is different. I want you to make sure you realize this is different now. The delta H of reaction can be solved for using bond enthalpies of the bonds that will be broken minus the bond enthalpies that are forming. So bonds broken minus bonds formed. Okay? It's not the same as products minus reactants. If you are given bond energies, you do it this way. If you are given enthalpy of formations, you do it this way. They are not interchangeable. So pay attention to the data that you were given in the problem, okay? So, what does that mean from a problem-solving standpoint? Well, let's take this equation right here. So here we're seeing methane reacting with chlorine to produce chloromethane and hydrochloric acid. Okay, so the reaction is taking place. Clearly there are some bonds that are being broken and some bonds are being formed. But in order to know what bonds are being broken and what bonds are being formed, sometimes it helps to draw a Lewis diagram so you can keep track of everything. So effectively, this is what happens. And I'm changing colors on purpose to show you the ones that are being changed. Not every single bond is being broken, right? Just the ones that are pertinent to this reaction. So, in this reaction, one carbon to hydrogen bond right here, one chlorine to chlorine bond is being broken. The bonds that are being formed, a carbon to chlorine bond and a hydrogen to chlorine bond. Bonds broken minus bonds formed. And when you have probably a table of values, you just plug in the values accordingly and solve for it. And so the delta H for this reaction will be negative 104 kilojoules. The difficulty with this is that it's so similar to what you use with the heats of formations that people often mix them up and they use the wrong one in the wrong context. So you gotta pay attention to the details. Okay, bond energies, you just do it this way. Heats of formation, do it the old way. Okay, so this chart here, we go from this much energy, and this much energy is input, right? This is your endothermic bond breaking process, increasing your energy. When the new bonds form, which is an exothermic process, right, the resultant energy is lower than where we started overall. So there's a net loss, hence this value has a negative delta H for reaction. Okay, so the next example. Let's calculate the enthalpy of reaction for the combustion of propane. All right, so combustion of propane. So first, what even is happening? What is propane? It is C3H8 plus O2. All combustion reactions produce the same products. You know this. Okay, so let's balance this. 3 carbons, 8 hydrogens. That makes for 10 oxygens on the right, so we'll need a 5 here. Okay. So, helps to draw out the structure so you know how many and of each there are. You could draw a Lewis diagram 3 times and 4 times if you want, but you know, basically you just have to keep track of how many there are. So you can do this one of 2 ways. You can figure out the difference in the number of bonds that are forming, or you can do them in a lump sum. Actually, no, they're all changing. We have to do all of these. So I take that back. So we have to figure out how many total bonds there are that are being broken. So what exactly is being broken? So we are breaking the carbon to carbon bonds. How many carbon bonds are we breaking? 2 of them. We are breaking carbon to hydrogen bonds. How many? 8. we are breaking oxygen to oxygen bonds. All 5 of them.
Does it matter if is there a different number for double bonds versus single bonds?
Yes. Yeah, the number is different. Okay, so that's our breaking. Bonds broken minus the bonds that are formed. So what's forming here? We got a carbon to oxygen double bond. How many of them are there? Careful. 6 of them, right? Because there's 2 per molecule. We have hydrogen to oxygen bonds. How many? 8 of them. Okay, so this is our setup. So now we just need to substitute and plug them in and solve. So the carbon to carbon bond, this energy, this is something that I didn't mention to you before because it wasn't relevant. But these energies are actually listed on your enthalpy chart. They're on the right-hand side. Bond energies, so they're already there for you, right? So let's go ahead and grab some numbers off of this. All right, so the carbon to carbon, 347. The carbon to hydrogen, 414. The oxygen to oxygen double, 498. The carbon to oxygen double, 715. And the hydrogen to oxygen, 464. Okay, so what's this all look like then? So 347 times, I don't need the times sign. 347 times 2 plus 414 times 8 plus 498 times 5, all of that minus 715 times 6 plus 464 times 8. Okay, somebody chug those out.
Negative 1,506.
1,500 what? And 6? Okay. Okay. One thing I need to mention about bond energies is that these bond energies are determined essentially through Hess's law-like reactions, and every value here in your bond energies chart is an average, okay? Depending on the situation, some of these bond energies might be in reality different than that specific circumstance. And this is because the bond energies change depending on the environment that that bond is in. So on your chart here, if I looked at a C single bonded to an O, on here, according to this chart, it says that it's 351. But what will affect this is what other atoms are bonded to that carbon as well. If that other carbon has other bonds, or if it has just lone pairs, the bond energies will be different. Not dramatically, just subtly different. Okay? So, when we calculate delta H reaction using bond energies, it is understood that there is going to be variance because we cannot isolate every single instance of each one of these bonds being broken, because usually these atoms are in the context of other molecules. Okay? So it's not going to be like perfectly spot on compared to the delta. If we calculated with delta H formation instead, you're going to get a value that's pretty close, but it's going to be off, and you should expect it to be off. Okay. All right. So some variance allowed. All right, so that is how you calculate delta H reaction using bond energies. So down here we're looking at a table that shows us relationship between the bond and the bond length. So first, if I see a carbon bonded to carbon, the bond length is given as 1.54 angstroms. But a double bond has a shorter length. A triple bond has shorter yet still. So the takeaway from this as the number of bonds between two atoms increases, the bond length decreases. Right? This is because as you have more electrons between nuclei, there are more attractions taking place. Right? So carbon, carbon. Here's 2 electrons. Carbon with 4 electrons in a bond. These are going to be drawn closer because remember, it's the nuclei that attracts the electrons. If there's more electrons between them, the nuclei has more to attract, drawing them in closer. And that's true pretty much with every element, right? Triple bonds are the strongest bond, and they're also the shortest. Single bonds are the longest, and they're the weakest. Okay, so hopefully that all makes sense. Okay. So we spent time talking about how to draw Lewis diagrams. What was the point of that? Just to be able to draw a Lewis diagram on a sheet of paper. The end game for Lewis diagrams is for you to be able to visualize what a molecule looks like in 3 dimensions. In order to do that, we're going to invoke VSEPR theory. Valence shell electron pair repulsion theory. If you think about this, these words should make sense together in context. Valence shell. We are talking about valence electrons because those are the electrons involved in bonding. Electron pairs. We're going to be paying attention to the number of electron pairs because they repel each other, and that is ultimately what determines the shape. So, if asked, what does VSEPR, what is the driving force behind it? It is that the best arrangement of a given number of electron domains is the one that minimizes repulsions, minimizes the repulsions among them. That is why molecules have the shapes that they do. So, let's look at the different families. The first thing you should realize about any Lewis diagram is how many electron domains there are. Okay? So when there are 2 pairs of electrons on the central atom, those are what we call 2 domains. An example, CO2 has 2 domains. Now those domains happen to be double bonds. That's okay. A domain is literally just an area where electrons are present. So that means a domain can be single, double, triple, or lone pair. That's what that means. Okay? If there are 3 electron domains, then the geometry, the base geometry is what we call trigonal planar, and planar means flat, right? You guys should know that from geometry, the word planar. Flat as in 2-dimensional. Examples. BF3 is a trigonal planar. Another example would be something like this. Sulfur trioxide, it's trigonal planar. It has a double bond in resonance, okay, but there's 3 domains and they're all bonded. What if you have a non-bonding pair? Remember we call these lone pairs? Non-bonding pairs are called lone pairs, colloquially, but technically they are called non-bonding domains, non-bonding pairs. So if you have a lone pair, that lone pair is still present, which is why the shape, the general shape of the electron domains is still the same, right? We still have 3 domains, and in order for these 3 domains to exist, they must space out, right? Be as far apart from each other as possible. The name of this shape, though, is going to be called bent, because the name of the geometry is based on the bond angles of atoms, not lone pairs. So that molecule is a bent line. It's not linear. Four domains. The shape of 4 domains is called tetrahedral. Tetrahedron means 4-sided. That's where that name comes from. Because if you think about it, it's a 4-sided pyramid. It's a 4-sided shape with the triangle base. Now, angles. You do have to know the angles. Let's back up. The linear angle, 180 degrees. Again, that is the bond angle. So that is the angle between the atoms that are bonded. Trigonal planar is 360 degrees divided by 3. So each one of those angles is 120. Now, this guy here, the bent shape, this angle is not exactly 120. And here's why. The lone pair is essentially, it's wider, it's fatter. So lone pairs take more space, which means the angles here and the angle here is not the same. It's close, but it's not, right? Normally, the angle would be 120, but in the case of a lone pair, this angle is going to be slightly bigger than 120. If that happens, then the bond angle at the bottom in green has to be less than 120. Exactly how much depends on the bonded atoms, but a fair number to use here would be something like 116, whereas these numbers up here would be approximately like 122. Does that make sense? Right, your total is still 360. Uh-oh. What happened? Houston, we have a problem. One second. I lost you. All right, there's a timeout on the field.